Hello everyone. In the previous video, we talked about how do we implement stack using arrays. In this video, we are going to talk about how do we do that using a linked list. So before we begin, let's just discuss why do we actually need a linked list implementation. We had already done that using using an array. So why do we need a linked list implementation? So if you remember in the last video, when we were trying to implement array stacks using arrays, we had to predefine a particular size for a stack. So we were doing something like hash define n and some number over here, let's say 100. And the thing is that in C++ or in any programming language, let's say Java also, you can only declare the size of an array to a fixed amount, right? Because the thing is, what are arrays? Arrays are nothing but continuous block of elements in the memory. And when we work with the memory, it does not it is not necessary that we always get a large chunk of memory which is continuous and free as well. Like even if in the ideal scenario we consider that the memory we have a lot of memory free, still the maximum size which you can go up to with the array is of the order 10 to the power 5 with the local arrays, and 10 to the power 7 if you declare the array globally, that too array of booleans. So that doesn't serve our purpose, right? So that's why we need a linked list, because we know that in a linked list we can have as many nodes as we want, right? Let me just clean this up. And the thing is that in a linked list we can have as many nodes as we want, and also the memory in the linked list need not be in a continuous fashion. Like it can be scattered, like one of the node is here and then it is connected to some another node which is here in the memory, and another node which is here in the memory. It doesn't matter what comes in between, but for arrays we always need a continuous block of memory, so which restricts our constraints in terms of size. So this is why we need linked list over arrays. So now let's just continue our discussion on how do we implement uh, the stacks using linked list. So what were the operations on the stack? If we revise again, so those were push, pop, top, and empty, right? And if we remember, whenever we were accessing array elements, we were doing that using a top pointer in the array. So similar is the case with the linked list. Even here we'll be having a top pointer. But in this case, instead of pointing to some indexes of arrays, what this top pointer will do is that it will be pointing towards a particular node of a linked list, right? So initially, let's say this is initially what will happen is the top pointer will be pointing to null, like it will be null itself. Since it is a pointer, so it can be null. Initially it will be null, indicating that the linked list that the stack is empty, right? So if the top pointer is null, it means that the stack is empty. And now let's come across each and every operation one by one. So let's see the push operation. How do we do a push operation? So what is a push operation essentially? It is basically nothing, but if we have this as a stack and we want to push an element inside of it, let's say a 1, right? So how will we do that using a linked list? So we'll first create a node, and as we know, a linked list node has two parts. One is the data part where it stores the data, and one is the next part. You can call it anything, but I like to call it as a next part, right? So what this does is it stores the address, stores the address to the next node of the linked list, right? So if we have, let's say, another node, if we have another node like this, and let's say its address is 1000 or maybe 2000. This is just a random number. Let's say I denote this address by 2000. So this previous node, and let's say these both two nodes are connected. This previous node will be storing this address, which is 2000, and this will be containing our actual data. Like if there has to be a one, so it will be one. If you want to insert a one in the stack, then it will be one. All right. So now, how do we actually build a stack using linked list? So let's just see that. So what we'll do is, like I said, we'll first declare a node, right? We'll declare this node, which will be having the both the data as well as the next part. And in the data of this node, we will put our data, whatever we want to insert. Like suppose we had one, so we'll be putting one over here. But then in general, you can say we'll be putting any number. Let's call that number as x. So we'll be putting x over here. And the next part, what we'll do is we'll make this next part to point to our top pointer, right? So this will be pointing towards our top pointer. And then what we'll do is this top pointer will make it equal to this particular node. So basically our top pointer will now be pointing towards this node. Okay, so let me just simulate on a particular data to make this more clear, and how this is working. So let me just first clean this up. So let's say uh, we had to insert some elements in the stack. So let's say we had to insert first a 1, then a 2, then a 3. We have to push these three elements. So what we'll do is initially we'll have our top pointer, which will be pointing towards null, okay, or which will be null itself, whatever you may say. So let's say it is pointing towards null. And now to insert the first element, which is 1, into the stack, we have 1, we want to insert it. So what we'll do is we'll declare a particular node, and what we'll do is we'll make the data part of it equal to, like, this is the data part and this is the next pointer, which will store the address to the next node. So what we'll do is we'll make the data part of it equal to the number which we want to push into our stack. So this will be 1, right? And now we'll make this particular uh, address part to point towards the top pointer. So this will be pointing towards what the top pointer is pointing to, that is null, right? And now we'll shift the top pointer to this particular node itself. So we'll do something like, let's call this node as n. So the top pointer will be equal to n, right? So n will come, the top pointer will come to this n. So our new top pointer is pointing towards this. Now let's say we have this already, and we want to insert another element into the stack, which is 2. So we have 1 already in the stack, and we want to insert 2 in the stack. So we'll follow the same procedure again. What we'll do is, let me just clean this up. Okay. So what we have so far is we have this node, right? And let's say we have something like this, and this particular node is right now pointing towards null. So basically this address has null, and this data part has 1. And now what will happen, and the top pointer is currently pointing towards this node. So we want to insert 2. So what we'll do is we'll create another node. We'll follow the same procedure. We'll create another node, and what we'll do is in the data part, we'll put 2 inside of it, and in the next part, we'll connect this node to the node which is already a part of the stack, right? Which is already a part of our stack, which is this node. So what is the address of this particular part? So this is nothing but whatever is pointed by the top pointer. So this operation will be something like, let's if this node is n1, so the n1's next part will be equal to top, right? Because top is the pointer which is pointing to the address of this particular node. Let's say this is n0. So this will have the address. We can assume it to be anything, like let's say the address is 1000, so this will have 1000 inside of it. So what we saw now, this 2 came inside of this stack. So what we saw is like we were able to add push a new element into the stack by creating a new node and then connecting it to the previous node. And now one more thing which is missing over here is like the top pointer is still pointing to the previous node itself. But as we have discussed so far, the top pointer should always be pointing to whatever is on the top of the stack. So right now it is pointing towards 1, but we have to move it to point towards the new element which has recently been added into the stack, which is 2. So what we'll do is like we'll make top equals to n1, right? So this n1, so this top from here it will go to here. And in a similar fashion, if we want to add another node, let's say, so what we'll do is we'll create another node and we will connect this node to this particular node. How will do that? How will we do that? By making, let's say this node is 2. So the n2's next will now again be equal to top, right? So suppose this had an address of 2000, let's say. So the address part of it will contain 2000, and the data part will be the new element which you wanted to insert. So let's say it was 3. So if you wanted to insert 3, so this will be the data part of it. And again we'll shift the top pointer from top equals to n1 to top equals to n2. So basically this top pointer will now be pointing towards n2. So this is how our push operation will work. Like in a similar fashion, we'll keep on adding nodes to the linked list in a backward fashion, and whatever the top pointer is pointing to is the recent element. And the last node of this linked list will be pointing towards null. So which indicates that if suppose we popped out all these nodes, so finally our top pointer will reach to null, which will indicate that the linked list is empty. So whenever we have a condition where top equals to null, that will indicate that the linked list is empty, right? Okay. So moving on, let's see the pop operation. So now what does the pop operation mean? It means nothing but just to remove the element which is on top of the linked list. So what is on which is on top of the stack? So what is on top of the stack right now? Or let's say what is on the recently added node to the linked list. So it is that node which contains the data part as 3 and address is 2000. That is the node which is pointed by top pointer. So now what we need to do is, like in array, if you remember, what we did was inside the array, if let's say we added some elements 1 2, let's say this was 4, so 1 2 4 and 3. Okay, let me just erase this, write it again. Yeah, so let's say we had 1 2 4 and 3. So the top pointer was pointing to 3, right? And whenever we popped, what I said was we just do a top minus minus, like we just decrement a top over here and the top will come over here, and we don't care as to what number is stored inside of this particular block of the array, right? But over here, if we try to do something similar, like if we move the top back again to this particular n1 node, like let's say we remove this top and we move it to here. So how do we move that? So we do that by doing top equals to tops next, right? So what is top right now? Top is this n2. So n2's next, what is n2's next? So n2's next is n1, which is nothing but the node with the address 2000, which is this node. And top equals to top next will we are essentially saying that top equals to n1. So basically top is over here. But in doing this, what happened? What just happened was that we lost the track of this particular node. So this is a bad practice. How? Because this particular node will lead to a memory leak, because we do not have any access to this particular node using any pointer as of now, because this is the only pointer which we are using to access the nodes, which is the top pointer, and we just lost the access to this node. So this will lead to a memory leak. So we need to make sure that before moving the top pointer forward, we are somehow able to delete this node from the memory so that there are no memory leaks. So how do we do that? So to do that, before moving the top pointer forward, what we'll do is we'll declare a temporary pointer. We'll call it as, let's say, a to delete pointer. It's just a name. So you can call it anything. You can even call it temp. I'm calling it to delete because we have to delete this. So it makes sense to call it to delete, right? And this to delete pointer will make it to point towards the top, which will be the current node, which we want to delete. And then now we'll be shifting this top to this one, this n1 node, and then we'll be deleting this particular node. How we'll be doing that? We'll be doing that by this reference to this node, which is to delete. So we'll simply do nothing, but we'll use the delete operation, uh, and we'll just delete the to delete node. To delete node, right? So this node will be gone for us, and the top pointer will now be pointing towards this particular node. So like this will be gone, and now only this much part is left. So in a similar fashion, we can again pop out this particular node and then this particular node, and finally we'll reach a condition when the top equals to null, and now we cannot pop further, right? Because for popping we needed to do something like top equals to top next. So in case of array, if you remember, when the array was empty, that is the stack was empty, which is also denoted with the empty array, the top pointer was pointing to -1, and we did top minus minus. So nothing will happen in that case. Like at worst, what can happen? Top will become -2, right? That is possible. But in this case, how we are popping elements, we are doing top equals to top next. But since top is already null, so there is no next to it, right? There is no next part of this null. So this will throw us an error. So we need to make sure that before we are popping, we have to check whether the top is null or not. If we want to, like prevent us from getting an error. So like this is how uh, we'll be popping our elements. So push is done, pop is done. Now next is top. So top is nothing but what it does is it just gives us the data which is present in the stack, like which is currently pointed by the top pointer as discussed in the previous videos itself. So in the top, we can just do something like we can return the top's data, right? We will simply be returning, like, let me just clean this all this up. So we'll simply be returning the data part of top, right? So suppose we have this node right here, and uh, we have the data part as 3. This is the data part of the node. This is the address part, which is the next pointer. So let's say it has some address like 2000, which is pointing to some another node. So what we'll do is simply we'll return the top's data, which will give us 3. So like if we have 1 2 3 in the stack, so we'll get our 3, right? This is how the top will work. We'll just simply return the top's data. Okay, so top is done. Now next is empty. So empty is again very simple. Like we'll just check whether the top is null or not. If the top is null, then the our stack is empty. If it is not null, it means that the stack contains some elements and it is not empty. All right. And one more function was there apart from all this. Let me just clean all this up. So one more function was there, which was size, right? So if you remember in array, how do we calculate? How did we calculate the size of our stack? So if we had this array in the array implementation method, uh, what we did was, if suppose the top is currently pointing towards this particular block of the array, so what we did was we simply returned top plus one, right? Because we knew that the number of elements will be nothing but one more than the current index which the top is pointing to. But in a linked list, there is no as such concept of indices, right? So for that, what we'll need to do right over here is we'll need to declare another uh, pointer, or let's say another variable, which will be called as size, which will keep track of how many nodes are we adding. So whenever we'll perform a push operation, whenever we'll be doing a push operation, and there will be some code over here, so at last we'll make sure that we increment the size, and initially like size plus plus, and initially we'll be setting this size to 0. And whenever we are popping from the linked list, so whenever we perform a pop operation, we'll need to make sure that we are decrementing this size as well, size minus minus, right? So in this fashion, this size variable will be storing the track of the size of the linked list. Okay, so this was all about the operations and the visual part of it. Now let's just jump to the coding part of it. Right. So let's just code out the actual linked list implementation of stacks. So the very first thing which we need to do is we need to declare a class called node, which will be nothing but it will help us to initialize the nodes of the linked list. And inside this class node, what all do we need? So the first thing is the data, obviously, which will be the data part of the linked list. And the second thing will be a pointer, which will be next pointer, node star next, right? And now we'll also declare a constructor. And yeah, we need to make sure that these both are public, right? Although this is not a good practice, because we all should always take care of encapsulation, the principle of encapsulation. Like this data should not be accessible to the user in any form. So for that, we should use getters. But for simplicity, I'm just making this as public, because later on we'll need this data and next into our stack class, which we'll be implementing. So yeah, instead of doing this as making this as public, you will make this as private, and you can declare two functions which will be nothing but getters of these, like the data and next, the getters for data and next. Okay. So yeah. So in the constructor, we'll be taking in the input as the argument as data, which will be the data which the user will give us, and we'll set that this data equals to data. So like this particular data of this class will be equal to the data which the user gave us. And the next will be initially null, because there are no nodes initially. So yeah, this was the node class. And now we'll be finally implementing a stack class. So what all do we need in the stack? All we need over here is not a dynamic array or something like that, because linked list, the size of the linked list need not be declared beforehand, or the linked list need not be declared beforehand like arrays. So here we'll just need a node star pointer of top, like a top pointer of type node star, right? Because what is it is doing is it is pointing towards a node, so it has to be a pointer of type node, so node star. So yeah, this will be private, right? So in C++, as I told, by default it is private, so you don't need to write something like this private. So I'll just leave it like this. So this will be private. And now One more thing which we need over here is like we discussed, we need a size variable to keep a track of what the size is, right? Size of the stack is. So now we'll declare a constructor over here to construct to initialize this top and size. So what will it be is that the top will initially be null and the size will be 0, as there is nothing in stack, so the size will initially be 0. So now let's just implement each and every method one by one. So what is the first method or the function? So it is the push, right? And it takes x as an input, which is nothing but the data which you want to push inside the stack. And now over here, if you remember in the array, we needed to check if a condition, if like the top was equal to n minus 1, something like that, because we had a fixed size. And if this was not the case, then we ended up throwing up an error called a stack overflow, right? But in this one, we don't need any such thing in linked list implementation, because there is no concept of stack overflow when we implement stack using linked list, unless and until obviously you don't like make a stack big enough which covers the entire memory of your system, of the hardware. So like yeah, in that case there can be a stack overflow condition, but then generally there won't be any such stack overflow condition. So now how do we do a push operation? So what did we discuss? We'll first declare a new node, star n equals to new node, and then we'll make the data part of this node equals to x, and then we'll make the next part of this node be equal to top, and finally we'll make the top equals to this particular node, like we discussed in the simulation which we did on the dry run, right? Or the dry run, I mean. So this was all about the push operation. Now let's just quickly do the pop operation as well. So the pop operation, again, like I said, uh, like in this case we will have to check if the stack is empty or not, right? Because we cannot pop from an empty stack, pop something from an empty stack. So how do we check whether a stack is empty or not? We simply check if the top equals to null or not. If it is null, then we'll simply throw out an error which will say something like stack underflow or stack is empty, whatever you want to call this, and we'll simply return from here. And then what we'll do is we'll declare a temporary pointer, like we discussed, a to delete pointer, to delete, which will be equal to the top, and then we'll be moving the top forward, so top equals to top next, and then we'll be deleting the to delete pointer, like we'll be freeing up the space, freeing up the memory, so that there is no memory leak. So this is how we'll be doing the pop operation. And push pop, so the next is top operation. So int top, so capital T, because the pointer is also named as top, they both can't have the same name. So even in this one we will have to check if the top is null or not. If it is already null, then definitely there is nothing to return, so we'll just return some garbage value as -1. And in this one we need to make sure that we return something, right? Because if we don't return, like if this statement is not over there, which was not in the case of an array, so what happened over there is we just simply returned some garbage value, right? Like it was something like the array of -1 was getting returned. So this was nothing but a garbage value. But in this case, you cannot do this. Why I'm telling you? Because here we are doing what we are doing is we are returning the data of the top pointer. But if the top pointer is null, there is no concept of data. So like there is no data inside. Like you cannot do something like null's data, right? Doesn't make sense. So it will throw you an error. To prevent this error, we need to make sure if the top is null, we return from here itself. So we'll return some garbage value, right? So yeah, let me just make this a bit bigger so that it is more clearly visible. So yeah, this was all about the top operation, and then we had the pool empty operation, which is very simple again. Nothing but we just return if the top is null or not. So if the top is null, it will return a true, otherwise it will return a false. And the last thing, the size function, right? So here simply we'll do nothing but we'll return the size, right? So the size will give us the size of the linked list. And how do we calculate size? So every time we push something in the linked list, what we'll do is we'll increment the size by 1 point. And every time we pop something from the linked list, so in this case, we are not popping anything, right? So if we don't put it inside of this if condition, but here outside of this, we'll just do a size minus minus, like decrement the size. And we should be good to go. So, and yeah, notice that I have written this S capital as well, because size and S and this size function and this size cannot have the same name. So yeah. So now we'll be declaring the stack, and let's do some basic operations, like let's push some elements inside of our stack. So stack dot push 1, 2, 3, and then we pushed 4, and then we'll just first see out, let's see if the size works fine over here. So we'll just do stack dot size, okay, and then we'll see out the top element of the stack. So yeah, and we'll be popping that element, and we'll do this a couple of times to see if it works fine. So like we popped out 4 over here, like we printed 4, popped out 4, printed 3, popped out 3, printed 2, popped out 2, printed 1, popped out 1. So at this particular moment the stack is empty, so we'll just check whether the stack is empty or not. So we'll just see out st dot empty, and remember that if else condition, like if this was giving me true, I returned a true, like return true, true. So I'll just use a ternary operator over here instead of that if else. So like what will it be is, if I'll check if stack dot empty is 1, then I'll output true. Otherwise, like how do we do this? If stack dot empty is 1, we'll return true. Otherwise, we'll return, okay, like it has to be like this. Yeah. So we'll return true. Otherwise, we'll return a false. Right. Simple as that. True and del, false, and a new line backslash. Yeah. So at this moment, it should return true. So let me just quickly write output as well so that we can check. So the size currently would be 4. Uh, Here it will give me a 4. It will give you a 3. It will give you a 2. It will give you a 1. This will give you a true again. And just to check the if the underflow condition is being followed properly, we'll again do a pop operation. So this should give me something like an error, like a stack underflow, and also after that it should be printing a garbage value which is -1, like returns okay, no, this won't print anything. Like suppose if I try to do something like stack.top over here, so again it will give me a stack underflow condition, and here it will be returning that -1 which we returned over here, right? So if everything is fine up till now, it should work. Let's just run. Wait, let me just do this. Okay, so there is an error over here, so I guess I'll have to enclose this within brackets for it to work fine. Okay, it says no matching function. Oh, okay. So like uh, over here, when I'm declaring a new node, so instead of doing this node data, like I made a constructor, right? The constructor for the node wherein we were passing the data. So if it was just a structure instead of a class in C, let's say if we had a struct where we are not allowed to make constructors, then we could have done something like that, like nth data is x. But over here, what we can do simply is, while declaring this new node, we'll simply pass in this x. So it will make sure that the new node is declared with x as the data inside of it, right? So yeah, now it should work fine, I guess. Yeah, there we go. So our size is 4 right now, like we discussed. So the size is 4. Okay, I printed size as well, so it will print something like size and 4, like it is printing over here. And then 4, 3, 2, 1, we have that. And then true, we have a true. And stack underflow due to the pop operation, stack underflow due to the top operation, and a -1 as well with the top operation, right? So this was all about the implementation. And just to check if the size is working fine or not, what I'll do is after 1 and 2 performing these two pops, I'll again check the size. So at this particular moment, they should return me a true, a 2, a value of 2, because like I popped 4 and 3, so 1 and 2 is left. So let's see if it works fine. Yeah, so it is working fine. The size is 2 over here, right? So yeah, this was all about the linked list implementation of stacks, and this was all about stacks in general, the basic idea of it. From the next video onwards, we'll be discussing few problems based on stacks. Like we'll be beginning with some basic problems to get an idea, and then we'll be moving on to some advanced problems. So see you then. Bye bye.